Hello everybody, this is Dr. Bricker here with Chapter 29, Part 2, and we've been talking about the hydrogen atom, and we can take a look at the quantization of angular momentum. We looked at energy in Part 1. We'll start with this video with angular momentum. So thinking back to Physics 220, the angular momentum of a particle in circular motion is mv times r, so go think back to Physics 220 for that. In the first part of Chapter 29, we talked about quantization of the de Broglie wavelength, and we looked at the distance around a circle, 2 pi r, had to be a multiple of the wavelength, so n times the wavelength. Putting in the de Broglie relationship for momentum, we came up with n h over mv. That has to be equal to n times the wavelength. So if you multiply both sides of this equation, by m times v and divide by 2 pi, this becomes mv over r, and that is the angular momentum. Okay, so same idea with the rest of the equation. So mvr turns out to be n h over 2 pi. So in other words, angular momentum is multiples of h over 2 pi. Right, h over 2 pi is just some number, and we're multiplying it by n. So you get 1 h over 2 pi, or 2 h over 2 pi, or 3 h over 2 pi. So angular momentum can only have those discrete values. We could use our new variable that we came up with last time. H over 2 pi is h bar. So angular momentum is just n times h bar, so multiples of h bar. Okay, so just like we have energy depending on n for hydrogen, angular momentum is the same thing. It's some multiple of h bar, and n here is 1, 2, 3. Okay, so depending on what state you're in, you'll have a certain amount of angular momentum. So this is again the hydrogen spectrum. Top rung of the energy level is the ionization limit. So that's how much energy you have here, 0. That's ionization means you completely have removed the electron. So if you start at negative 13.6, if you want to completely remove an electron from hydrogen, you have to provide 13.6 eV of energy to that electron, either in the form of a photon or in the form of some other particle that comes in with at least this much energy and knocks the electron loose. Okay, so according to the Bohr model, the frequency of a photon when you go from state n to m is the difference in energy times h. So what does this come from? Remember, the energy is h times f. If you solve for f in that equation, you get the difference in energy over h. Okay, so this is not really new. We saw this sort of equation back in Chapter 28. The difference is now we know how much energy the nth state has, and we know how much energy the mth state has from last time. Okay, good. One nice thing about this is the hydrogen spectrum. So if you have a hydrogen spectrum problem on the homework or the test, you know right where to go, what equations to use, what concepts to use. You know right where to go to for that. Okay, very good. Okay, and then we could write this equation in terms of the wavelength. Remember, the speed of light is the frequency times the wavelength. So just going back to the previous slide. You can take this for frequency then and put in that relationship, that the speed of light is the frequency times the wavelength. Solve for frequency, do a little bit of algebra, plug it in here, and you get the wavelength of a photon emitted when you go from n down to m. So remember, n is larger than m. So you're transitioning from a higher state to a lower state. So from an n state to an m state. So the wavelength, when you do that, that's what this notation means. Wavelength going from n to m, speed of light divided by the frequency, turns out to be wavelength naught, that's what the 0 means, divided by 1 over m squared minus 1 over n squared. Okay. And that really turns out to be the Balmer formula that we saw before. Remember when we first started talking about this, the Balmer formula, Balmer came up with it just based on behavior. he didn't know anything about the underlying physics behind it. So this is the underlying physics behind it, looking at the transitional energy of a photon. And it's the exact same formula. This wavelength naught is 91.1 newtons times meters. Okay, so this is the formula that will give you the wavelength of transitioning from N to M. Okay, great. So Balmer came up with a formula to just describe what's going on. This is the physics behind it. Okay, so this figure shows two series of transitions that give rise to wavelengths in the spectrum. The Balmer series is when you transition to the M is equal to 2 state. Okay, and this is visible light. It's light that you could actually see with your eyes. It's in the Roy G. Biv spectrum, so the wavelength correspond to that. There's actually the Lyman series too. This is ultraviolet, so you can't see this with your eyes. So you're transitioning from a higher state down to N is equal to 1. And this you can't see with your eyes. Balmer series you can see with your eyes. Here's an example we can take a look at. Okay, let me read it here. When astronomers look at distant galaxies, they find that light has been strongly absorbed at the wavelength of the 1 to 2 transition in the Lyman series for hydrogen. Okay, this absorption tells us that interstellar space is filled with vast clouds of hydrogen left over from the Big Bang. What is the wavelength of the 1 to 2 absorption in hydrogen? Okay, so photons are passing through this gas. We have an absorption going on, and electrons are jumping up from 1 to 2. So then that's missing from the spectrum. Think back to what the absorption spectrum looks like. You see all the wavelengths, and there's some that are missing. So they're saying, what's the wavelength of the missing one when the electron jumps up from 1 to 2? Okay. So we can take a look at the new formula that we just had, going from 1 to 2. This equation predicts the absorption spectrum of hydrogen if you let M equal to 1. The absorption spectrum seen from astronomers is from the ground state of hydrogen, M is equal to 1, to the first excited state, N is equal to 2. So we can put the numbers in here, 1 and 2. Be careful, this is nanometers. Solve for it and you get 122 nanometers. Again, that's not in the visible spectrum, but this is ultraviolet. This is the wavelength that you would see, or you wouldn't see. Far into the ultraviolet, ground-based astronomy cannot observe this region because the wavelengths are strongly absorbed by the atmosphere. But with space-based telescopes, on the other hand, first used in the 70s, astronomers see the 122 nanometer absorption. It's nearly identical in every direction that they look. So astronomers have come to the conclusion that most of the universe is actually made of hydrogen. This is the line that's seen in every direction that you look. Okay, very good. So next section, quantum mechanical hydrogen atom. So Bohr's model worked well in explaining the hydrogen atom, but did not work for other elements. So hydrogen is a good place to start because it's the simplest. Once you start adding more protons, more neutrons, more electrons, things become more complicated. And it was 1925, so 100 years or so, Schrödinger introduced the theory of quantum mechanics, capable of calculating the allowed energy levels in any spectrum. So this is sort of a thing where we know how to do it, but the underlying idea of why is this happening still hasn't really been found. So the Bohr hydrogen atom was characterized by a single quantum number, n. Schrödinger's analysis of the hydrogen atom found that it must be actually described by 4 quantum numbers. So n's a good place to start. We're going to have another one called little l that describes angular momentum, and then you'll see there's a couple of magnetic quantum numbers too. And in just a minute, you'll see how this is related to chemistry, how different shells fill up in hydrogen. So we know this. So if you're talking about hydrogen and you want to know something about the energy, this is the formula for the energy levels. Minus 13.6 E divided by n squared. And we have that nice ladder energy diagram. Okay, so ground state, negative 13.6. The next one would be negative 13.6 divided by 2 squared. And the next one after that, negative 13.6 divided by 3 squared. So this n is referred to as the principal quantum number. It turns out that the angular momentum, as we saw at the beginning of this video, is also quantized in terms of the orbital quantum mechanical number. Angular momentum is L, and then times the square root of L plus 1, this whole thing under the radical, times h bar. And here, little l could be anywhere from 0, 1, 2, 3, all the way up to n minus 1. So if n is equal to 2, L can be 1 or 0. If n is equal to 1, L can only be 0. So it's always 1 less. And it takes on a series of numbers. So again, for example, if n is 2, L could be 1 or 0. It doesn't just have to be 1 less. It could be 1 less and even more or less. Okay? Those are the allowed angular momentum values. The plane of an electron's orbit can be tilted, but only at certain discrete angles. So each allowed angle is characterized by another quantum number called m. And this is the magnetic quantum number. And this depends on L. So it's sort of builds and builds and builds. We know what n can be. Now we know what L could be. It's n minus 1, etc. And then we've got another one here called the magnetic quantum number, which ranges from negative L to 0 up to positive L. So for example, if L is equal to 1, m can be 1, 0, or minus 1. If L is equal to 2, m could be 2, 1, 0, negative 1. Just like that. That's how it works out. So there's a range of values for m, and m is based on L. L is based on n. Okay? And then we've got one more called the electron spin, and this can be spin up or spin down, it's called. So when m is plus a half, that's called spin up. When m sub s is equal to minus 1/2, that's called spin down. Okay, so we'll see how that works out here in just a second. Let's look at this example. List all the possible states of a hydrogen atom that have energy of negative 3.4 eV. Okay, so first thing we need to do is figure out the principal quantum number. And looking back at the energy formula, we can do that. Okay, let me show you where this formula is actually coming from that you see on the screen. Energy is minus 13.6 eV divided by n squared. So n squared, solving for n squared, minus 13.6 eV. And the energy that they're telling us is negative 3.4 eV. Whoops, hopefully that looks okay. Negative 3.4 eV. So to get n, you just have to take the square root of this. So n square root of negative 13.6 divided by negative 3.4. That's where this formula is actually coming from. So n turns out to be 2. This is the n is equal to 2 state. Now if you looked at the energy diagram, you could just look at it and see when the energy is negative 3.4, that's where n is equal to 2. This is how you could actually solve for it. Okay, so if n is equal to 2, what can L be? Let's look at the next slide, actually. So when n is equal to 2, did I say negative 2? When n is equal to 2, I meant L can be 1 less than 2, so L could be 1 or 0. L can't be 2 or greater than 2. It has to be 1 less than the n, which it would be here, all the way down to 0, or it could be this one. Those are the allowed states. Okay, so if L is equal to 0, the only possible value for m then is 0. Remember, think how m goes. Negative L, etc., 0, all the way up to positive L. Okay, so it just depends on what L was. So again, here, if L is 0, the only thing that m could be is 0. On the other hand, if L is 1, then m can be 1, 0, or negative 1. So there's 3 different values for m there. And then for each of these states, we could have a spin up So m sub s is equal to plus a half, or m sub s is equal to minus a half. Okay, let's make a little table of all this. I think that's on the next slide. Yep. Okay, good. So here's the way to look at it. When n is equal to 2, L could be 1 or 0. Let's look at on this table when it's 0. Well, if L is 0, M can be 0, and you could have a plus a half here, or same thing, 2, 0, 0, or negative 1 half. This row here corresponds to L being equal to 0. Okay, what happens when L is 1? When L is equal to 1, then we could have M being 1 with the spin up. Same thing here. N is 2, L is 1, M can be 1, and then spin down. When N is 2, L could be is 1 in this case. M could be 0, and then we have spin up and spin down. And we also know when L is 1, M could be negative 1, and then spin up and spin down. So these are the 8 possible states that we have. It all starts with N, and then you've got to figure out what L is, and then the possibilities of L. And then once you know the possibilities of L, you know the possibilities of M, and then attached to each of those is a spin up and spin down. Okay, it takes a little bit of getting used to. It's not too bad though. Okay, so maybe from chemistry you've seen this table here. This SPDF, the way shells fill up. It turns out that S corresponds to L being equal to 0, P being L is equal to 1, etc. When L is equal to 2, the symbol is D. When L is equal to 3, the symbol is F here. So the hydrogen atom depends only on the principal quantum number. However, for other atoms, the allowed energy depends on N and L. So for hydrogen, we know the energy just based on N. So the ground state of hydrogen is equal to, when N is equal to 1, in that case, L can only be 0. Same thing, when L is equal to 0, as you saw on the previous slide, M can only be 0, and then you have spin up, spin down. So in the ground state, there's 2 possible situations. So think about how a hydrogen shell fills up in terms of electrons. There's 2 possible spots there, and that's what this is, spin up and spin down. For N is equal to 1, L is equal to 0, M is equal to 0, and then spin up, spin down. Okay, so that's the 1s state. I think you've seen that in chemistry if you've taken some chemistry. On the other hand, the 3d state is more complicated because you've got a lot of different values for the different quantum numbers. Okay, let's take a look at another table that describes this. So here are the principal quantum numbers. Here's 1. So this is the ground state. It's 1s. When n is equal to 2, think of all of the possible quantum numbers that you have when n is equal to 2. L could be 0 or 1 there. This corresponds to 2s. This is 2p. There's the energy. When n is equal to 3, L could be 2, 1, or 0. Here's the 2. Here's the 1. Here's the 0. Same thing when n is equal to 4. L could be 3, 2, 1, or 0. And that's where you see all of these. So that's the way the shells fill up. So for chemistry, probably you were just told maybe S, P, D, F. But there's a direct tie-in to quantum mechanics, and it's the way, starting with the principal quantum number, all the other states we can describe them just based on that. Okay, and it all comes back to this energy level diagram. There's a lot of layers here, so it's sometimes hard to keep track of. You might have to watch this a couple of times to let it really sink in. Okay, so we've got the rules of what these different things can be, though. Okay, so the electron's orbital angular momentum is quantized, and we see the different values here. This is the total amount then. So just based on the L quantum number, you can get what the angular momentum is. And it's just multiples of h bar then. Okay, so when let's look at how we get these different values. When L is equal to 0, plug in a 0 for little l. Turns out to be 0 then, because you would be taking 0 times something, you get 0. On the other hand, when L is equal to 1, so put in little l equal to 1. 1 plus 1 is 2 times 1, that's still 2. You get the square root of 2. When L is equal to 2, that's where this one's going to come. Little l is equal to 2, put a 2 in there. 2 plus 1 is 3 times 2, you get 6. Don't forget the radicals there, etc. So these different values, those are the only values of angular momentum you can have, and they're based on plugging in 0, 1, 2, 3 for little l to get the total angular momentum. Okay. It says down here, an interesting prediction is that the ground state of hydrogen when L is equal to 0 has no angular momentum. A classical particle cannot orbit unless it has angular momentum, but a quantum mechanical particle can. It's kind of mind-boggling to think about that, but that's the way it works out in terms of quantum mechanics. Okay, good. So a little bit about electron spin. We learned previously that an electron has an inherent magnetic dipole moment. Think about an electron, which is a moving charge. Moving charges produce magnetic fields, and it acts like a tiny bar magnet. And if you want to think about it like this, think of a chunk of metal that makes up a magnet. What if all the electrons were spinning in the same direction? Moving charges produce magnetic fields. Those magnetic fields in metals all sort of line up with each other, so the magnet has magnetic properties for that reason. That's the way I like to think about it. And in terms of quantum mechanics, it's not exactly the correct way. It's not exactly what's happening, but for all intents and purposes, if you think about it like that, you get the correct answer. So I think about electrons moving around the nucleus, producing magnetic fields. They're all lined up with each other, and that's why a bar magnet's magnetized. It's, again, more complicated than that, but if you think about it like that, you get the correct answer. It also has intrinsic angular momentum called electron spin. And just from the last section, there's spin up or spin down. So if an electron's going this way, you might say that that's spin up. The electron's going the other way, it's spin down. And you can tell which is which by putting the electron in an external magnetic field and seeing if it flips this way or flips that way, depending on what the external magnetic field is. So again, spin up and spin down, just depending on which way it is. Okay, so there's two possibilities, either spin up or spin down. Okay, now let's take a look at this example. Which state of hydrogen has this energy? So they're telling us the energy minus 13.6 divided by 9. Okay, well, we know the formula for this. It's minus 13.6 divided by n squared. So here the n must be equal to 3. Okay, good. So when n is equal to 3, these are our two choices, right? That's what the number in front of S, P, D, and F means. It's the principal quantum number. Okay, and angular momentum, square root of 6 times h bar. So remember what angular momentum is. Square root of L plus 1, h bar. So we want the part under the radical here to be equal to 6. So L plus 1 has to be equal to 6. So we can just kind of, if you want to, put some numbers in and see what we get. When L is equal to 0, that does not give us 6. When L is equal to 1, so I'm talking about little l here. When little l is equal to 1, we don't get 6. When little l is equal to 2, let's see if that works. So little l equal to 2. 2, and then 2 plus 1. That's the one that's actually equal to 6. Okay, so little l then is equal to 2. So go back and think about the SPD. SPD. This when L is equal to 0. This is L is equal to 1. One was L is equal to 2. Okay, good. So what we have to have here then is 3. And when we have L is equal to 2, that's D. So this has to be 3D. The 3 coming from the principal quantum number, L is equal to 2 corresponds to D. So 3D. There we go. Good. Now I explicitly solved for little l here. You already saw on a previous slide when the total angular momentum is the square root of 6 times h bar. From the previous slide, you just saw that that was L is equal to 2. Here I just actually solved for it for us. Okay, good. So that's the state that we have to be in. This is the 3D state if this is the energy and if this is the angular momentum. Okay, good. So that's a good little example problem, I think. Okay, the 3D energy level in hydrogen has how many distinct states with different values of quantum number m? Okay, so 3D, this is the one we just did, that was L is equal to 2. So they're saying, what can m possibly be? So think about what m can possibly be. It can be negative L, so negative 2, and then that would be negative 1, 0, all the way up to positive 2. So those are the possible values of m. And then each of those would have a plus or minus 1/2 on spin. They're not asking about that here, though. So m could be 5 different things. So when little l is 2, m could be negative 2, negative 1, 0, 1, and 2. So 5 different ones. Okay, good. Little synopsis there. Okay, so the rest of the slides are just kind of a summary of it. We'll stop after this section for Chapter 29. If you have any questions, send me an email. I'll talk to you soon. Bye-bye.